All right, today we're going to talk about optimization and modeling in section 4.3. We'll be using two class periods to discuss this section. This is one of the more important sections in this semester. And this is about finding and maximizing and minimizing quantities of real-world problems, perhaps. So let's start with an example. Let's ask, what is the largest rectangular area that one can enclose along a riverbank with 100 feet of fencing. So imagine you've got 100 feet of fencing and you've got property along a riverbank, and you want to enclose a rectangular area along the riverbank, and you want the largest possible area. Right. Okay, so this is a problem, right? We got to figure this out. Now, we could call this the length and that the width of the enclosed area. And the question is, do we want pretty even like this, or do we want really long but not very wide? Or do we want very wide and not very long, right? Those are all possibilities. And perhaps one of these possibilities is going to contain the most area. Now, area, as we all know, is length times width, right? Now, if we tried to use calculus right now, we'd be stuck, right? The problem is we've got two variables. We don't know how to do calculus with two variables. We only know how to do calculus with one variable. However, there's always in these problems one way of eliminating one of the variables. And the way we do that is with this key situation here of 100 feet of fencing. Not only is the area length times width, we know 100 is the same thing as the length plus twice the width. Right, because we have the total length of the fencing is one width, the other width, and then the length. So we get length plus twice width. That allows us to eliminate a variable, right? L is equal to 2W, excuse me. L is equal to 100 minus 2W. So now we can make the area a function of the width only. The length, which is 100 minus 2W, times the width, which is W. That's the variable for the width. Now we have a nice function, 100W minus 2W squared. This is a function we know how to maximize now because of the previous section. So indeed, we can take the derivative. A prime of omega is going to be 100 minus 4W. And so the critical point is going to be W equals 25. And that tells us that A of W, or A of 25, is the maximum. Why do I know it's the max? Well, when A at 0 is equal to 0, and A at, what's the other? A at 50 is equal to 0. These are both fences with no area, right? If you use all your fence for length or all your fence for width, you're going to enclose no area. So this must be a max. And what is it? A of 25 is 100 minus 50 times 25. So it's going to be 50 times 25, which is 1,250. Do we have units here? Feet. So this is be square feet. And that's the largest possible area we can enclose with just 100 feet of fencing. Okay, so this is the first example of one of these problems. The common theme you're going to get when you're working with these word problems is you're going to get a nice function for the thing you want to maximize or minimize. And then there's always going to be another function relating to variables that you'll use to eliminate one of the variables in the first function. Okay. Let's take a look at a different one. This one's not a real world example, but it's actually a little bit more difficult. Here's the question. The sum of three numbers is 36. And I forgot this, non-negative numbers. One number is twice one of the others. What is the maximum possible product of the three numbers? Okay, we've got the sum of three non-negative numbers is 36. What is the maximum possible product of the three numbers? And one number is twice one of the other numbers. Okay, so now we have to just kind of search around and find some equations. Let's call the numbers A, B, and C are the three numbers. I know that A plus B plus C is 36, all right, because the sum of the three numbers is 36. And I also know that one number is twice the other. So let's say that B is twice A. It doesn't matter whether I say C is twice A, B is twice A is twice C. It doesn't matter which one we pick. We just got to pick one and be consistent there. And we want to maximize A times B times C, right? That's the quantity we're trying to maximize in this situation. Okay. When we do that, we have A. B, we know, is 2A. And C is 36 minus A minus B. So we got that from here. All right? And we got that B is equal to 2A from there. I want to eliminate that final B as well. 36 minus A minus 2A. So this is going to be 2A squared times 36 minus 3A. And when we put that all together, we get 72A squared minus 6A cubed. Okay, there's our function that we're trying to maximize. Now we can take a derivative of this 72A squared minus 6A cubed. And when we do that, we get 144A minus 18A squared, and we factor, we get A times 144 minus 18A. Okay, A equals 0 is critical, but clearly that's not the right answer, because if A is equal to 0, the product of A, B, and C is 0. So that's not what we want. A equaling 8 is the other answer that we get from there. It's also critical. When A is equal to 8, we get A is 8, B is 16, and then C is left with 12 using this fact that A plus B and C is 36. And when that is the case, we take 8 times 16 times 12, and we get 1,536 is the max possible product of three numbers whose sum is 36 and one of the numbers is twice the other. Okay, I want you to try your hand at some of these. We'll be doing several more examples over the next 2 class periods, and I hope that it prepares you well for the homework assignment.